Well, here we're asked how to find the x and y intercepts of any generic function defined by y equals f of x. Well, I think maybe the first place to start is just to do a quick sketch of some generic function so we can visualize what it is we're trying to think about here. So here's a function, and we'll call that function f of x. So the x-intercepts would be these points here where the function hits the x-axis. Well, to see what's going on here, we think about what value do we know for sure is occurring there. Well, we know that the output is 0 there, or y. So every place on the x-axis, we know that y or f of x equals 0. So to find the x-intercepts for any generic function, you simply set y or f of x equal to 0, and then you need to solve for the x's that make that true. So I'll just go ahead and write it as f of x equals 0 and solve. The y-intercept's a little bit easier here. We know since it's a function, there's only ever going to be at most one y-intercept. And if we think about what's going on here, we know that the y-intercept is occurring where on the y-axis where x equals 0. And so for y-intercepts, we simply need to put 0 as the input. So 0 is the input, which means evaluate f of 0. Notice how these are in fact different here. A lot of students get those confused and think they're the same thing. In one case, we're putting 0 in as the input. That's for the y-intercepts. In this case, we're setting the output equal to 0 and finding what inputs give us that output of 0. So graphing functions, so basic graphing of functions is a skill every Algebra 2 student should have. This first one here, there's lots of ways we could attack this one. One is we could notice that it's a line and go for the y-intercept and slope approach. But just as an introduction, I'm going to just think about that table of values approach that we've talked about in the past, where we just take some inputs. So I'm going to put an x here. We're going to choose some inputs. I'm just going to pick some in the middle of the graph here, -1, 0, 1, and 2. And then we need to evaluate what f of x is for those inputs. So for -1, if we put -1 in for x, I'll do that down here. -3 times -1 plus 1, so this is f of -1. That's going to equal -3 times -1 is 3, plus 1 is 4. If we put 0 in, f of 0 is -3 times 0 plus 1. That's going to just be 1. And so on. I'm not going to finish those off, but if we kept doing those, we'd get 2 more values, and then we can go ahead and just plot those values and connect them. So the first one is -1 and 4. That's up here. 0 and 1 is right here. 1, -2 down here. 2, -5 is further down. And not surprisingly, since we expected it to be a line, it's a linear function, we can see the line. Note how you could have also gone for the y-intercept. This is in slope-intercept form. We can see that that is 1. It's not a coincidence that that's 1 because of the slope-intercept form. And then we could also go, we see that slope here is 3, or sorry, -3. So we could, from the y-intercept, we could go, if rise over run, we could rise -3, 1, 2, 3 over 1. Rise -3 over 1. Okay, second one here, we see k of x equals -2. This is just a constant function. So that means no matter what I put input in for x, -2 is going to come out. And so that one's a relatively simple one to graph. It's the constant function where no matter what the input is, the output is -2 or a horizontal line. Number 10, this is the square root function. Again, if you don't have a vision of these functions, it's probably best to start off with a table of values. Since it's a square root function, we know that no negative inputs can go in, so we might as well start with 0, because anything negative will not produce a value, because there are no square roots of negative numbers in the real number system. So 0, square root of 0 is simply 0. That one's pretty straightforward. If I put 1 in, I get square root of 1 is p of x, which equals 1. And then I could put 2 in. We'll go ahead and do that. Square root of 2, that doesn't have a nice value. You could look it up or on your calculator. You think it's about 1.4. But we could also be smart about what we put in, since we know this is a square root function. I could do 4 as an input, because that'll give us a nice value when we take the square root. P of x is the square root of 4, or 2. So I'm going to go ahead and graph these 3 nice looking points, 0, 0, 1, 1, and 4, 2. And if we wanted to tuck this one in here, we could do that too. 2, 1.4 is about right there. And we get the familiar looking square root function, which you should actually now recognize as 1/2 of a sideways parabola, but and which is what it is. And then number 11, this is an absolute value function. Hopefully you have a vision that this is going to be some sort of V-shaped type thing. So we'll go ahead and just create a table of values to go ahead and find out where that's occurring. -2, -1, 0, 1, and 2, just some points in the middle of the graph. Absolute value of -2 plus 1 is -2 plus 1 is -1. When I take the absolute value of that, I get +1. Here we have the absolute value of -1 plus 1. -1 plus 1. Remember, you have to evaluate what's going on inside the absolute value first. So -1 plus 1 is 0. If I put 0 in here, 0 plus 1, absolute value of that is also 1. And 1 plus 1 is 2. The absolute value of 2 plus 1 is 3. So now we have points we can plot. -2, 1, right here. -1 and 0 is right there. 0 and 1 is right here. 1, 2, and then 2, 3. And we can see the V shape that we were expecting. And looks like we did pick the right spots to get the cusp here. So that's one dimension, or one side of the V. And here would be the other side of the V. And that is the graph of the absolute value of x plus 1. For number 12 here, we were asked to evaluate the function at 5 different points. For this video, I'm only going to show one of the points, as the process would be the same for all the other values. So what we're going to do here is just do r of -2. So this means tell me the output when I put -2 as the input. So r of -2 is I'm going to replace every x with -2. So -2 squared minus 2 times -2 plus 1. So you can see what I've done here is every place there's an x, I put -2, and then I just go ahead and evaluate. -2 squared is +4. -2 times -2 is +4. We have a +1. So r of -2 equals 9. One thing I'll point out here is sometimes what students will do on this one is they'll write the equation like this: -2 squared minus 2 times -2 plus 1. And there's a subtle difference here. Notice how I wrote it with no parentheses. And the reason this is important is if you actually put this on a calculator, this -2 squared, evaluate this in the calculator, you'll actually get -4, because remember, the squared only applies to what it's immediately touching. It's not really touching the negative sign, it's only touching the 2. So if you did this, you would get an answer like -4 plus 4, and those would cancel out and you'd get 1. But that would be a wrong approach. So it's really important to make sure you think about putting those parentheses around that value when you do the evaluation. And then, again, I'm not going to do the other 3. It's the same process. The answers are in the answer key. And then for B, what is the domain of R? Well, domain is the allowable inputs. And remember, when we think about domain, we start with the presumption that anything will work. So we want to think about, do all real numbers work here? And then think about illegal operations that might result, which like dividing by 0, taking square roots of negative numbers. But in this case, all we're doing is squaring a number and multiplying by -2. So any input we put in, those are valid things to do. So the domain here is going to be all real numbers.